Hi, Josh.
No, so this is the Zacchini problem. So it's been iterated in many physics textbooks for a
Okay,
very long time.
you want me to read the problem? The Zacchini family was renowned for their human cannonball act, in which a family member was shot from a cannon using either plastic elastic bands or compressed air. In one version of the act, Emmanuel Zacchini was shot over three Ferris wheels to land in a net at the same height as the open end of the cannon and at a range of 69 meters. He was propelled inside the barrel for 5.2 meters and launched at an angle of 53 degrees. If his mass was 85 kilograms and he underwent constant acceleration inside the barrel, what was the magnitude of the force propelling him?
Here's Emmanuel Zacchini
Ah,
and his
yes.
brother. Here, this. So here's the main figure. Will not be necessary mostly because we're not using. We don't care much about the parabola. So first, the figure one. So first, we will draw the free body diagram. So this is the main vector. So basically, it's force over here. And then there's a y component, which we will name Fy canon. And an x component, uh, which we will name Fx canon. So of course, the angle here is 53 degrees. Because of course, who's propelled inside the barrel, an angle of 53 degrees. And then there is an extra force, which is of course gravity. So that is his mass, which is 85 kilograms times g, the gravitational acceleration. This figure 2. So now we will need to write down a few kinematic equations because you can never live without writing at least one of these. So here, y minus y0 equals v0 yt, or the velocity at the start component, with the y component of the velocity at start. It's minus one half. Was supposed to be acceleration, but now since there's no other acceleration in the y direction, only gravitational, so we'll be using the gravitational acceleration g, p squared, and then x minus x0 equals the x component of the start velocity, or v0 t, equation 2. So here I'll be using this for the rest of the problem. Variables highlighted in yellow are known. So this is v0y is equal to v0 sine theta. This is a trigonometric application. So the y, of course, is here. So the sine is the opposite of the triangle. Then here, v0x is equal to v0 cosine theta, because the x direction is the adjacent of the right triangle, and then we will just be dividing it by the hypotenuse. Of course, it's number 4. Okay, so from 1 and the given, y minus y0 is 0 because, as it says in the problem, uh, he was propelled. Wait. Zacchini was shot over 3 Ferris wheels to land in a net at the same height as the open end of the cannon. So it means his end height is the same as the start height. So it means y minus y0 is 0. Okay. So the next we put 0 here from 1. And we substitute v0 sine theta using 3 times t final, or it means the time at which he lands, minus 1 half gt f squared. Okay. So we are going to find his force. So what we're aiming for is to find his acceleration because we know his mass. And we need to know his direction too. This equation 5. So using 2, equation 2, its range, which is 69 meters, r is equal to v0 cos theta using 4 times t final. And that's it. Equation 6. For equation 7, we'll be needing to isolate V0 because we will need velocity later on. So now we're going to isolate the start velocity slowly. Then now we have isolated TF first because we do not need to isolate V0 right now. We can do that later. So TF is equal to the range over V0 cosine theta. So now we have an expression for TF. Now we can substitute it into 1. We can use all of this that we now know and use TF because we know how it is in terms of V0 and range, which we know range, cosine, and theta. So we know range and cosine theta. We only don't know V sub 0. So we'll be able to isolate later. So now 0 is equal to V0 sine theta times R over V0 cosine theta because that is TF. And then here, we can now cancel V0 and V0 because they are like. And then now minus 1/2 GTF squared. So now we have an expression for TF. So we can substitute this in equation 8. This equation 9. And then therefore 1/2 GR squared over V0 squared cosine squared theta because we have expanded this. Because it's hard to work with parentheses, we just expand this. It's not very hard. So it's equal to R sine theta over cosine theta. Why? Because we already canceled this V0 and V0. So now this is one big expression. And then we move this onto the other side. So this is number 10. Then isolating V0 squared. Now we can isolate it because everything is known. We know R, we know G, we know, of course, the constants, and we know theta. So we know cosine theta and sine theta. So that's nice. We can now isolate it. This is isolated form because we will only need to transpose V0 squared cosine squared theta and then so divide the rest and then divide cosine squared theta again. This is how it looks like. And then now we can simplify this. And then we can simplify it even more by removing the extra R. And this is a very, very nice hack because we know that we must know, I did not write it here actually. We must know the trigonometric identities for the double angle. So 2 sine theta, cosine theta, that's going to be sine 2 theta. So we know what's going to happen, GR over sine 2 theta, nice. So we use the double angle formula. Now we have a much cleaner formula for V0 squared. We don't need to take the square root right now because we don't need V0 alone because it won't occur as a single variable. It needs to be squared. So by Newton's second law, we can use this for figure 2. Where is figure 2? Here. So figure 2 is illustration where Fy canon, Fx canon, and then subtract the gravitational force. So we'll be using components. So now our F net is equal to Fx I hat. I hat is the x component plus Fy j hat because it's the y component. Where's the figure 2? I did not put it here. Sorry. So we'll remember to put that next time. So here is Fx and Fy. They're both facing in the positive x and positive y direction. And then mg, the gravitational force, facing in the negative direction of y. So it must be subtracted. And of course, it's in the y direction, so it should be j hat or the y component. So here, minus mg j hat. So now Vx, which is the velocity in the x-axis, is equal to V0 cosine theta. This is because we already have this formula, V0 cosine, where is it? Here. Number 4, V0x is equal to V0 cosine theta. And we also have a Vx formula. So now we can simplify it. Similarly for Vy, it's just Vy equals V0 sine theta because it's the sine part of the triangle that we're taking. And then now we have similarly for the direct displacements. X is equal to d cos theta and y is equal to d sine theta. What is d? D is the length of the cannon. So the length of the cannon, not really the length of the cannon, more like the length of the cannon in which the Zacchini was propelled from. So that's 5.2 meters. It's not necessarily the length of the entire cannon. Just the length of the hole which it was in. So there, we have y minus y is 0. So this is just equation 1. And then we're going to substitute now for the vx squared formula. So we have the vx squared formula. It's nice. So now we have we know d, we know theta, so we know this term and we know that term, which is of course just a constant 2. And then now we have ax. So now that we have the now that we're getting the acceleration, it means that once we get the value, we can get the force because it's just force equal to mass times acceleration. So eventually we will get to the force. Substituting 4 into the previous equation, we can expand Vx in terms of known variables, which is V0 and cosine theta. So now, we know everything except Ax. So now we can get Ax. First, I'm going to isolate it. And then for Y, we can do the same thing because nothing changes. And then we can isolate it. Okay, so now AY is isolated. AX and AY are both isolated and we know everything on the right side. So now, it's time to substitute. So substituting 13 into 21, we can now expand V0 because we don't really know what it is. There, so now we have GR over 4D sine theta. We know G, we know R, we know D, and we know sine theta. Nice. So note that 13 was used in for the reason that 13 contains cosine theta in the denominator. So it would be much easier if we just use 13 instead of using the other one, which we would still convert back into 2 sine theta cos theta. So similarly for AY, we can do the exact same thing, just replacing every mention of x with y and changing the sine into cosine. No, the cosine into sine. Because here in the x component, cosine was used, and in the y component, sine was used in what formula? In equation 4, I think. Wait, I cannot scroll. There, in equation 4, cosine was used. In equation 3, sine was used. Okay, finally, we can substitute the given values into 26 and 27. Now we will have the accelerations, AX, which is 40.7 meters per second squared. And we have the equation for AY, and we also know the right hand side. And substituting, that gives us 54.0 meters per second. Okay, now we have the accelerations for X and we have the accelerations for Y. So all we need is the equations for force, which is remarkably easy because by the figure 2 over here, we already know the directions of force. So now we can do the complete formula for the force experienced by Zacchini, which is F net, or the net force he experiences, which is his mass times his acceleration in the x direction, I, because the x component, plus his mass, again, times his acceleration in the y direction with the y component, g hat. So in the terms we used earlier, that is Fx canon I plus Fy canon j minus his gravitational force, the gravitational force he experiences. So this is in what direction? J. So since it's in the y, it's in the y-axis. So now simply we can just group all of together of the we can group together all of the x the forces along the x-axis and the force along the y-axis. So that's just distributing the j hat. Because of the simple fact that all terms with I hat and j hat must be equivalent, because of course it means every force going in the x direction should be equal to the forces going in the x direction, which makes a lot of sense, of course. So for the y direction, it's the same thing. Every force moving in the y direction is of course equivalent to every force moving in the y direction, because that's not what it is. So now we can equate all of those. So now we are left with Fx canon, which means the F of the cannons, or the force of the cannon going in the x direction, and the force of the cannon going in the y direction. And we know everything on the left hand side, and we know mg, which is on the right hand side of equation 33. So we can now isolate them and substitute. Note, we already know the acceleration and the acceleration of we know the acceleration of Zacchini in the x direction and the y direction, but the precision earlier was only up to 3 digits. So if we use those values, we will be left with only 2 digits. We could have left another digit, but it would be much more precise if we use the values we used earlier, instead of using a totally new equation. So now, substituting all of the values, we get Fx canon is equal to 3460, or 3460 newtons. And then substituting for Fy canon, that is 5420 newtons. So now we have the forces in the x direction and y direction. We only need to find the combined force, which means its actual force heading in only one direction. Using the Pythagorean theorem, why did I put formula? So anyway, we can finally calculate the magnitude of the canon without any components. The F canon is equal to the square root of 3460 squared plus 5424 squared. I place an extra 4 here because it's an extra significant digit, so we will be left with 3 significant digits once we end. So this is equal to 6430 newtons. And then finally, for his actual direction, it's the direction of the force, not really his actual direction. His true angle of force, so the angle that the force exerted on him is actually taking, not 53 degrees, because 53 degrees is only the inclination of the cannon, not his actual force. So theta is equal to the inverse tangent of the y component of f over the x component of f, because the forces are in a triangle. So we're going to take the angle here, theta, by using the opposite side and the adjacent side. So that must be tangent or cotangent, but it doesn't really matter. So tangent inverse of fy over fx using the values is equal to 57.46 degrees. So now we know his force, now we know his angle. So the problem is solved. QED. So there you go. This is force.
Nice. Congrats. Nice solution. Very ordered.
Yes.
Organized. Thanks for
Thanks for
watching.
watching.